Hello, guys. My name is Yinghai Lu, and we are from MZMETRICS team from Machine Zone, and our team includes Siva, Igor, Vibhav, Sujesha, and me. And today we're going to talk about a little bit about high-performance Erlang pitfalls and solutions. Basic agenda is like the following. First, I already talked about what we do with Erlang in Machine Zone, and we will extend to talk a little bit about what are the issues and roadblocks we met during our project, and some of the generic lessons we have learned in terms of pushing the performance with Erlang. And we'll share some of our profiling techniques, and in the end, we will focus on a specific case study with a high-performance counter, which will be given by Siva. At the Machine Zone, we use Erlang currently we are building a high-performance data processing system. And when we started this project, performance is one of the first-order priority in our objective. So we are thinking about how to make it fast. One of the typical designs that we started is a pipeline tasks. For example, we have requests coming in from one node, and we have a receiver collect all the requests, and we push it to another processor, which does some logic processing. And when we get the result, we'll put it to the sender, which dispatch all the result to the different nodes. And it's kind of natural to map all these three components onto different processes in Erlang. It works well for a while. And next, then when we push to the performance, when we increase the scale, and then we met with some problems, and we are thinking about how we can exchange data faster between processes. One of the solutions is the Erlang term storage, which is kind of like a shared data structure used for communication between processes. One process will get a key and put a value with this key, and another process will use the same key and get value from it. So we were interested in what the performance is with this ETS table. And for example, we set up a experiment here. The experiment is like this. We want to update the count of certain keys, and we increase the number of processes from 1 to 16, and note that there are two critical lines here. This line is the number of physical cores in our machines that are being experimented on. This is a 4-core machine, and this is the other line is a number of logic cores. And we are kind of expecting the performance to go like this, because we're approaching the number of logic cores. We're expecting the performance kind of saturates, and when we approach the number of number of logic cores, I think the performance will definitely saturate. So these are the kind of the update operation performance we are expecting. And when we really run the test, we got a result like this. So as the number of process increases, when we kind of go steady up, then instead of saturate and keep a high level like this, the performance has a sudden dip, and with increased number of processes, we just have a worse performance. So this is an experiment on 10 keys. So we're kind of not convinced, and we tried a different setup. So we do 1 key, 10 keys, up to 1,000 keys. As you can see, 1 key is the for one key, the performance is really bad because everybody is trying to contend for this one lock for this key. And as the number of keys grows, we are getting better, but we still have this kind of dip after we use up all the cores in our machine. The reason for that is that the ETS table has locks. So although it's fine-grained locks, it's kind of what it does is kind of partition all this storage space onto different tables. By default, I think it's 64 since Erlang 16b. And however, when we are trying to, when a lot of processes trying to acquire access a lot of keys, there's still locks going on, and this can be traced from, with like a GDB tracer, which we will discuss a little bit later. So next is message passing. This is like most like natural way of program in Erlang, right? So we pass one message to another process. And we are also interested in how efficient, how much messages we can push from one process to another process, or from M process to another M process. Here we have an experiment. We have 10 senders and 100 receivers, and we are trying to figure out how much message we can send and receive among a period of time within 1 second. And we run it for a while, and as we can see, the number kind of like wiggles around 3 million per second. Next, we try to be more generic, and we increase the number of senders from 1 to 100, and we increase the number of receivers from 1 to 1,000, and we observe the number of message we process. As we can see, yeah, depending on different scenario, it's kind of different. But our experiment, we use a MacBook Pro. Where, it's kind of like the best we can do is below 10 million per second. So don't get me wrong, this is actually really good. We tried a lot of other message passing frameworks, and it's really difficult to beat Erlang in a generic setup. And for Erlang itself, I think why we have this limitation is that when we are adding messages from one process to another process, it requires a lock on the message queue. And furthermore, when the process run off message, and when it is activated by another incoming message, the scheduler has to do a lot of new scheduling. For example, you have to add it to the run queue, and this involves a lock. And if the process is running out of messages to go to sleep, and the scheduler will try to steal from other scheduler, and which also involves locks. So all these locks kind of give us an overhead. All in all, what we observe is that on a fairly modern MacBook Pro, we can have this limitation about 10 million message per second, and we did it on a pretty powerful 56-core server. The limitation is a little bit higher, but it's around 22 million. So what we are thinking about is, can we achieve more? Can we break like 22 million on a server, or 10 million on a MacBook? Before that, I think the optimization thinking is that are we solving a much more difficult problem? So do we really need to pass so many messages between the processes? So the first step in our optimization is to minimize the message change. So we do our design ourselves. So we know that maybe there are some slack we can borrow. For example, at first we introduced this three-stage pipeline design. What if we merge the receiver and sender into the processor, and we put everything on one process such that we don't need to pass the message from the receiver to processor and from the processor to the sender. And in addition, we can partition our request to do the sharding, and we can avoid the communication between all these shards. So by limiting the number of message exchange, we really can help us a little bit by solving an easier problem. So here is a kind of like a toy example. So now we are eliminating all the communications. We are purely doing all the suppose we are doing purely the computations and how fast it can be. Without and the experiment here is that we keep doing the small computation with us, and when we finish without passing or receiving any message, we go to the next loop, and we are interested in how many loops it can finish within 1 second. And the experiment setup is kind of the same. We start with one process on the node, and we gradually increase the number of processes from 1 to 100. And as you can see, as the number of processes increases, we kind of like wiggles around 80 million instead of like have a sudden dip. And note the absolute value here. It's like 80 million. It's like 100x of the ETS experiment we did, and it's like 20x to 30x the max exchange with like the first design we have like 3-stage pipeline. This is the first one. Is like before we solve it, try to reduce the problem like from application level. And the second one is message batching. So suppose we are trying to send 1,000 message from process A to process B. So instead of invoke, send, and receive 1,000 times each with one message, can we do like invoke, send, and receive only 10 times, and each time we send a batch of 100 message? So we repeat the experiment we did with 10 sender and 100 receivers, and this is the and we also put in the unbatched solution as for comparison, and they are shown as the dotted lines below, and as we can observe there are clearly a huge gap between the batch and unbatched solution. And to be more generic, we also repeat an experiment with senders from 1 to 100 and with receivers from 1 to 1,000. As we can see, there are clearly gaps between dotted lines and the solid lines, meaning that, and overall, we can observe a 5x to 30x like more message passing rate per second, depending on the different configurations. And we talked about how to reduce the problem, how to do the message passing, and then the third solution is domain-specific operations. So what I mean is that as an engineer, and we know the specification of our product, and we know what the communication pattern is going to be. And so instead of using all those generic logs and stuff, if we understand the problem we're going to solve, we can try to devise some log-free structure, which is faster. So for example, in our project, we have this requirement that have this application that we have one processor who is delivering a lot of message to multiple recipients. So in this kind of setup, we can actually, we have a situation of one writer and multiple reader kind of situation. And we can actually explore some more efficient log-free data structure. So for the sender side, we can have a process receive all the requests. We do some processing, and after we get the result of the processing, we can put it into a shared memory data structure, which is lock-free. And from the receiver perspective, we need to devise the similar way to read from this lock-free data structure and actively polling it. So Erlang doesn't provide a generic way of solving this, so we did this by implementing our own NIF functions. And note that we actually don't want to have all the processes, receivers busy spinning and waiting for the message to come and waking up and sleep. So we also designed our own notification technique to reduce all this waiting time. In this setup, we actually achieved a throughput of 600 million messages per second on a 1-to-many setup. So next, I'll talk a little bit about some of the generic lessons we learned during our process of optimizing a Erlang application. First up, try use sharding. One of the first problem we saw in our system is that when we just begin our optimization, we found that when we push the load, increase the load, and we will have some node that has increased latency and increased memory. And we figure out that there's all the request is coming into this one process, and it's just not fast enough handling all the stuff. And it's getting laggy, and after a while it gets switched out by the scheduler, and all the message queue backed up with increased memory. So so the solution for that is avoiding having a single process handling everything. Instead we use a pool of non-communicating shards, and we have all the requests with kind of key. And we do Erlang PH2 on the keys and distribute them, try to distribute them evenly onto different shards. And after that, the bottleneck is gone. The second lesson we learned is actually about data structure. As we know, hash map is is very generic kind of a data structure in our software engineering, and Erlang itself provides us with a quite wide spectrum of hash map containers, among which we have ETS set, we have the new Erlang maps, and we have the process dictionary. So we are actually curious about the performance of all these containers. So we did some experiments. This experiment is about how fast we can fill up a container. So the experiment is like this. We have ETS set, we have maps, and we have process dictionary, and we try to insert 500 million elements into the containers respectively, and we try to measure the time it takes. Obviously, the less time it takes, the better it is. So we observed that in this experiment, process dictionary is a little bit better, but the advantage is not very obvious. However, we did our next experiment. So what this experiment is about is that we have already a field container. So we pick Erlang 18 maps and Erlang 18 process dictionary for comparison, and we increased the number of already allocated keys from 1 to 100K. And what we are interested in is we keep picking one random key inside and updating it, and we are interested in the number it takes for 100K updates. As we can see here, at first they grow kind of similar and even even the maps is better. And after maybe I think 33 or 32, I think the Erlang maps changed its data structure, and then afterwards the gap begins to show. And however, in the meantime, the performance of Erlang process dictionary is pretty stable. So I know that it's kind of like a more natural thing to put the map into your state of your Gen server, but for like performance critical applications, we tend to use process dictionary. The third lesson we have learned is about the limitation of our number of processes. So at the lesson 1, we said that we don't want to rely on one process. However, we also don't want to have like an unlimited number or arbitrary number of processes. The reason for that is that when we create process, there is some kind of like cost with it. Although we know that Erlang process is like lighter weight than the Linux process or Linux thread, there's still some cost to associate with that, especially when we create a process and when we do the process resolution. We have this one global pick-to-proc lock, and when we did this experiment, that when we launched like 100K process at the first, then you observe a freezing period of time in Erlang VM that nothing moves. Then afterwards, things begin to move. Then at the end of the experiment, we destroy all the process, and you will observe a similar kind of thing, like a freeze in Erlang VM, and this will result like a spike in latency. And what we did is we try to have fixed number of processes, and we try to distribute all the work among all those fixed number of processes. The third topic about here is about how to do the profiling. As we can see, we're a performance guy, and one of the key thing about performance is measure. And however, what we need to pick our profiling tool carefully. One of the criteria is that we want the measuring tool to be low overhead, because if it has more, because a lot of our applications are timing sensitive. If we have like a high overhead in measuring, it kind of like shifts the landscape of how the system works, and sometimes you get a different picture. So yes, the criteria is low overhead. And the first like kind of very handy tool we use is pstack. What it does is when you type pstack with the process ID, it will print all the stack trace on all the thread of your Erlang VM. And by glancing this or screening this quickly, you can check whether I have a lot of locking happening, whether I have a lot of scheduler like idling or doing like nothing. Pstack comes with the GDB package, and what you need to do is like do pstack and PID. And if you don't have pstack, you can emulate it quickly with a do GDB attach processor and do thread apply and all, and backtrace and add the trace stack length. So the second tool that we actually use the most is called EEP. I know that it means a little. It means like Erlang enhancement proposal for most of the guys. But actually here it means Erlang easy profiling. I guess when our colleague Igor developed this module, he didn't know what it is. As I said, it's developed by our colleagues, and it's actually based on the GDB module with relatively low overhead, and the usage is quite easy. and it will produce a call grind-based compatible file, which you can use for visualization and easy analysis. The usage is very easy. So it contains 3 steps. First, you collect the runtime data. What it does is you have, for example, you have a Erlang process running, and you do the attach and get your remote console on, and you do start file tracing, for example, ABC, and for example, you need to sample it for 10 seconds, and you want to stop. It will produce a file called abc.trace. Then the second step is to do offline analysis. What you can do is you can have this file anywhere and bring your Erlang console anywhere. Then you do the convert, and it will convert it into a call grind compatible file. The third step is visualize and analysis. Here we have actually an example. So this is a K-cache grind visualization of a Erlang application. As you can see here, they give you a lot of information. It gives you how many times a Erlang function is called, and how much self-time it consumes. And it also gives you the call stack for you to trace who is calling this repeatedly. And what we basically do is we look at this graph and we kind of figure out how to improve the system. Last but not least, we use system level profiling. Here we use oprofile. I think also there's some other tools like perf. The reason we use this is that we have some NIF functions in our system, and sometimes we want to go to a deeper level to understand what's going on inside NIF. And oprofile itself is very powerful. It has a lot of functionality, but the most simple way of doing it is first initialize your oprofile, then fire up your oprofile with your test command. Then it will generate a report, and you collect the report and do the visualization. Kind of same thing. Here is an example about what kind of visualization it is. It's kind of a call graph, and what you want to focus on is the highlighted boxes and the paths. For example, here we find that we trace along this highlight path. I found we have kind of a lot of unexpected memory allocation here, and probably our NIF is doing something funny. So I want to bring the stage to Siva here, because in terms of performance, mirroring is also is very important. And one thing about mirroring is that we need to count a lot of events. And during our development, we found that a lot of counters doesn't suit our need. So we have a project to develop a high performance counter here. So let's welcome Siva.
Hi everyone. I'll talk about a specific problem we solved at Machine Zone. It's basically counters. We tried to use some of the existing counters and we faced a few issues. So we decided to implement our own library. Before I show the implementation, I want to compare the existing libraries and then show some of the bottlenecks and then move on to our implementation. So the reason we need this high performance counter library is we have millions of events happening in our system on one single system per second, and some of the counters are like very frequently updated by hundreds or thousands of processes, and we need a very good approach to this contention problem of where many processes update one single counter. The libraries we used are exometer, falsum, and then I put ETS in also, like we try to use the ETS update counter API. Exometer in itself has two kinds of counters. One is exometer native counters. It's implemented using ETS tables internally. And then there is another counter called exometer fast counter. It's supposedly very fast, but the exometer native counter beats it at scale. And then ETS, we just use the ETS update counter with one single table across the whole system, and that doesn't seem to scale well. So coming to our benchmark environment, this is the...
I'm getting confused. Did I understand correctly that the exometer is implemented using ETS?
Yeah. Exometer native counters uses ETS tables.
So then why do you say that ETS doesn't scale?
ETS doesn't scale. So exometer native counters, it uses per scheduler ETS tables. But the ETS I used was one single whole table for the whole system.
Okay, but that's the ETS you use.
Yeah. Yeah, that's what I'm pointing out. If I use one single ETS table, it doesn't scale. If I use many ETS tables like exometer uses, it scales well. So this is the benchmark environment I used. Our platform had 2 CPU sockets. Each CPU socket had 14 hardware threads, and then each hardware thread has 2 hyper-threaded CPUs on it. So in effect, it's 56 CPUs on our system. And the Erlang runtime was 18 with SMP enabled. Here are the results for the existing libraries. Like you notice, if we compare for just one single process, ETS table performs really fast. But then once we start using many number of processes that update this single ETS table, it doesn't seem to scale. Exometer fast counter, it starts out really good, but then once we move on from 2 processes, it also degrades. So the exometer counter, it starts a little lesser than exometer fast, but then after moving on from 2 or 4 processes, it scales pretty well relatively. And obviously, exometer native counters are the winner here by a large margin. Just to repeat what I said, exometer counter scales well, but it seems to be very slow just to update a counter. And fast counters doesn't scale well. The reason ETS doesn't scale well seems to be that there is a lock contention in ETS table. The solution we came up with was to implement our own metrics library. It's called MZMETRICS. We took the per CPU kind of table approach exometer had, and we tried to optimize it in our use case. So before I move on to our implementation, I want to explain the per CPU data structures we used and just kind of a refresher for you all. Just a refresher on Cacheline. Cacheline is just a chunk of bytes in the main memory. Like say, on x86, it's about 64 bytes. So addresses 0 to 63 fall in one cache line, and then 64 to 127 fall in the next cache line. So when a CPU tries to modify a byte, it has to fetch this whole cache line and then modify. It cannot just address one single byte at a time. Now I want to, before I move on to per CPU, I wanted to just show some fault sharing with Cacheline and show the effects of it. So in this example, there are 2 CPUs, CPU 0 and CPU 1. They are trying to CPU 0 is trying to modify struct foo, and CPU 1 is trying to modify struct bar. They are totally independent, but then unluckily, the 2 structures fall in the same cache line. So initially, if we assume this is the state, the cache line is in the main memory, and both the CPUs haven't yet touched this cache line. So if CPU 0 initially fetches the cache line, this cache line is duplicated in L2, and it also goes into internal CPU 0. CPU 1 issues a fetch, gets it into its L2, and it is also in its L1. Now, say CPU 0 issues a write. It has to send a write or invalidate request to main memory and also the other CPUs that have this cache line shared. And then the other CPU, CPU 1, has to invalidate ACK back, and then the ACK has to go back to CPU 0, and only then CPU 0 can actually write to it. So until now, it has to be waiting for this cache line to be present in its memory. Now, say CPU 1 wants to access this cache line, which is present in CPU 0's L2 cache. CPU 1 issues a write request, which goes to main memory, which gets converted to invalidate, and then CPU 0 has to invalidate, send it back, transfer it to main memory, and also transfer it to L2 of CPU 1. So the reason it's called fast sharing is that conceptually these two processes are not really sharing anything, but because the two data structures are in the same cache line, it ends up as if they are sharing some data structure. So to summarize, this is from an old article on LWN. They tried to do 500 million counter updates on a quad-core system. So if they try to do a single counter update, like if all the CPUs try to share the same cache line on the same counter, the whole bar shows the time taken for 500 million updates. But when they try to split it across multiple cache lines per each CPU, the blue bar is the one that's the amount of time taken per each CPU. Obviously, blue bar is very small relatively. And now if we consider the difference between the total bar and the blue bar, the red bar is the overhead of actually all the CPUs using the same cache line. Another thing I want to point out is, like, if we consider the effects of QPI, quick path interconnect, this effect will be even higher because the quick path interconnect bandwidth is much lesser. While we are on this topic, I also wanted to point out one more thing. Intel transactional memory. There is a new feature called lock elision in Intel hardware, which is currently disabled because of some hardware bugs. But once we support this in Erlang VM lock implementation, we will not be needing finer grained locks in smaller critical sections like, say, ETS. But again, this is disabled on x86 because of hardware bugs. It's implemented in glibc, but I think Erlang VM, it doesn't have it yet. So coming to our metrics implementation, our design is basically based on per CPU counters, and we used an if. We used atomics to update the counters. In our library, creating a new counter, it requires a lock. Deleting a counter requires a lock. And then read or update counters, there is no lock required here. It's an atomic operation. Now to compare the new library we implemented versus Exometer, the top bar is the new library that we implemented, and if we compare, this new library is almost 10 times faster. If we look at the point in blue bar, it's at 48 processes trying to update one single counter. It shows that if there are 48 processes trying to update one single counter, Exometer counters takes 1 second, but then the new library takes just 0.1 seconds. Now, to put that in perspective, if you think of a system with 48 CPUs, Exometer almost uses one whole CPU to just update counters if there are 1 million counter updates on the system. But then with our new library, we almost free up that CPU. We have pushed our source code here at github.com/machinezone/MZMETRICS. So in conclusion, we we showed that we found message passing to be expensive when we try to do it at a massive scale. And we also showed that there is, when we create a large number of processes, there is a log that seemed to be causing a contention. And we were not able to use existing libraries for fast counting, so we had to come up with our own implementation. So just to summarize the solutions, what we suggested until now, we said sharding is very useful in many instances, and then try to limit message passing when we are trying to do it at a very high scale level, or even batching them. And when we are trying to create like huge number of processes, it's better to limit the number of processes than trying to create thousands of processes and then figuring out there are contention issues. And lastly, our MZMETRICS counters are really fast. Thank you, everyone. We are solving some really hard problems at Machine Zone, and we are looking for people to join us. If you are interested, you can go to machinezone.com/careers. All right, thanks.
So you guys are, relying on a lot of NIF calls for both communication across processors as well as for updating like internal shapes of state. Are you seeing scheduler collapse involved during this process? Like, what's going on?
Yeah.
So your question is, if we call NIF a lot, do we observe any scheduler issues in Erlang VM? Let me think about it.
We have seen scheduler issues. We haven't been even able to measure exactly what kind of problem we're seeing, but we see that there are processes that are being scheduled out and cause latency. But we have not really been able to properly measure the scheduler level of what the issues are.
I mean, do you see this scheduler worker just die though, where like you had 56 active work queues and then eventually 30 after a while?
No, because whenever the issue is observed, it traces down to the bug we have in NIF. After we fix that, we try to keep the NIF as the NIF call itself as short as possible. So after that, we didn't really realize any problems in scheduler. But maybe there is, but we cannot directly pipe it from with the scheduler NIF.
Okay.
Can you maybe can you estimate how long your new functions consume? I need the time, maybe some microseconds or some milliseconds.
It depends on, I guess it depends. For the counter library, say it's just a few cycles where we atomically update a counter. But
so
then
it must be a very, very fast one. That's on your conclusion.
Yes.
It depends on the library.
Some of the NIF calls, most of the NIF calls we are doing is a few microseconds. We're not spending a whole lot of time in the NIF. So maybe somewhere of the order of between 5 and 15 microseconds what we see. So we don't do a lot of complex operations.
Can you elaborate how you are notifying the receiver when there is data in the NIF? Like when things have been pushed into the NIF, how the receiver knows there is something to process?
We implement our own notifier, and the kind of key is that we don't notify every time for every message that comes. So we kind of do some micro batching. So because we don't want to wake up all the recipients
So you're using message passing to notify, but not,
Yeah, we to notify, but not to pull the actual data. Yeah.
For your map versus process dictionary benchmark, was OTP built with MRTs native? Do you know
mean with native lib flag?
Minus MRT equals native for GCC.
I don't think we did that.
We didn't do that.
We can try that again.
Yeah. Okay.
Well, I think you should probably revise that.
Okay. Thanks.
Any more questions?
This is a more general question. Well, this I understand as an implementer that you would like to have this type of micro benchmarks and draw some conclusions from them. But you also probably want to have, especially since you are doing this for your own application, something that is representative of your application and measure there how much better you are with one solution than the other. So you want, I think, to also create a benchmark that sort of is representative of what the real application is doing.
Yes, we do
Because
have.
then you might see totally different numbers.
No, so we do our own benchmarking we have our own benchmarks for our application. I mean, these were more for optimizing the performance at the lower level. But we also have our benchmarks on the application level that we do on a daily basis to see where we are compared to other solutions. So do we have that? Not presented here.
Yeah. Because, for example, there is no real application, you just send message and does nothing else. Why do you send this message if you're not in your processing there or doing some other computation in the meantime?
Yeah, I guess we can talk about this much more later. Maybe next year we can present it better. But we have application level benchmarks that kind of measure the performance of the application itself. And that will show where we are compared to other solutions. So maybe next year we can present it.
All right, I think that's time. Thank you.
Thank you.